Hello and welcome back to the third video in the series on data science for doctors. So let's get started. This is all about the basic statistical tests that we will be learning today. It will be a targeted approach. I'll make sure that I keep it quick, short and to the point, and I'll tell you about the most commonly used tests, the easiest approach to do that and to interpret them. So the outline includes, we will be discussing core concepts of tabulation, how to basically visualize data, and to pick and choose the types of tests that we need. We'll also be looking at union, bivariate or multivariate tests, just introduction. Then how to choose the appropriate outcome, because every test depends upon the outcome that you choose. So it all starts with the outcome in my mind and how it should actually when you're analyzing your data. Then we'll be understanding bivariate tests for continuous or categorical outcomes, and then we'll finally get to do these tests. So first, let's start with this core concept of tabulation. What is this? Now, whenever you have a bunch of data, for example, let's say you have got a variable A, you've got a variable B, and you've got a variable Y. So you've got three variables. Now, how to visualize that? Now, the best way is to make this 2x2 contingency table. So this is how you can visualize. You should keep your outcome on the y-axis. Like in this case, y is on the y-axis, and you should keep all the predictors, like in this case A and B, on the x-axis. Now in this case, as you can see, A is a continuous variable, that's why it's represented with a histogram, and B is a categorical variable, it's represented with a bar chart. But you can keep multiple continuous variables or multiple categorical or a mixture of them, like in this case on the x-axis, and you can keep the outcome or the outcomes on the y-axis. And this is basically to get started. Now all the tests that you will perform will actually depend on what you keep on the y-axis, whether it's a continuous or a categorical variable. So let's go ahead and see and understand what I meant by saying that. Now, before we understand about that, let's understand a quick thing about univi or multivariate tests. So univariate tests are, we've already explained them before, mean, median, and mode, and all of those descriptive statistical things that we've done in the earlier video. Bivariates are the ones which we will be looking at the moment. So as explained earlier, for example, in this case, gender is present on the x-axis, and CSE, which is basically calcium scoring system on the coronary vessels, for example, is a continuous variable and it's present on the y-axis. So we've got essentially two variables, gender and CSE score, and the relationship between them or any test that we perform will be called as bivariate tests. Now, so let's understand that in a bit more detail. Now, the same concept as we explained before, the same table consisting of CSE score on the y-axis and gender on x-axis. Now if you generate two of these tables and divide this based on the race of the population, like in this case Asians versus non-Asians, now we are looking at three variables at the same time. We are looking at CSE score, we are looking at gender, and we are looking at the race as well. And we are analyzing three variables at the same time. So what have we done? We have analyzed gender, basically CSE score across gender, and we have adjusted this for the race. So this is basically called as the adjustment or adjusting for a specific variable or confounder. So in this case, for example, Asians or non-Asians, which is basically the race variable, was a confounder. So how we would adjust for this confounder is by actually making two tables independently or running two analyses differently, separately, and then seeing whether the results of these two analyses was same or not. Now, so this is one of the ways to adjust for confounders, but the other best way, since this is basically adjusting for categorical confounders, like for example Asians or non-Asians, but what about if there was a continuous confounder or continuous variable? So the best way to adjust for the continuous or categorical variable is to use different types of regression techniques, which we'll see in the upcoming videos. But this was just a quick understanding of what is uni, bi, or multivariate analysis, or how to use multiple variables to analyze data. Now, The next thing is to understand how to choose an appropriate outcome. There are several things that you need to consider. Some of them have been listed here. So first, you should know that what you're looking for, yeah, and what you want to know about that variable, and you should be clear yourself. Now, for example, in this earlier example, we had a CSE score. So we wanted to see or predict the CSE score, or the coronary artery calcification score in a given patient, because maybe we thought that this was important and it was a good predictor by itself of coronary artery disease. And we wanted to predict that score based on gender, whether males or females have a higher CSE score. So in this way, we should at least be able to be clear ourselves about the whole concept and the outcome, and we should know what we're talking about. Secondly, is it feasible to quantify and compare the outcome? Now, in the same example as we're talking, now, CSE score quantification requires a proper CT scan. So you should be clear about this fact, that whether you can do that or not, is it feasible, and the fact to compare it across different populations, whether do you have this data for different sexes available. In the same way, the third question is, how clinically significant can this outcome be? Is CSE score clinically significant? Does that really matter? Has it been proven to play any important roles in coronary artery disease in any of the papers prior to this? So you should know about these things, whether this is clinically important to take that as an outcome or not. And then the fact that, do you have sufficient predictors that could explain this outcome? Now, in this case, we just have gender. We can add multiple other predictors to predict the CSE score, or to find whether the CSE score has any impact on coronary artery disease. But again, you should be having sufficient predictors to predict that kind of an outcome. Now, the last point is about the hard endpoints or outcomes. And this is one of the most important points, in my opinion, that you should be looking for. Now, what is a hard endpoint? A hard endpoint is something which actually matters in case of these research projects that you're running, which can be mortality or morbidity markers of a given patient. Now, CSE score can be called as a surrogate marker of coronary artery disease, which is basically not the actual marker. But in this case, or in its place, if you would have put the coronary artery disease presence or absence, that would have been a hard endpoint. But even better would have been the effect of CSE score or similar variables on the mortality of a given patient, whether all of this actually predicts the mortality or not. So that could have been a hard endpoint. So it's always the best idea to come up with hard endpoints or outcomes and use them as your outcomes. But if you don't have them, then you would have to go with the other outcomes that are available. So continuing on to the same journey, so let's have a look at different types of outcomes. The first one, we've already discussed, that CSE score being the continuous outcome on the y-axis and gender on the x-axis, and we can get a similar table like this one. And the second type of outcome that we should be looking at is the categorical outcome. So in this example, we can see that mortality, so that's one of the hard outcomes that I was talking about, whether a patient died or he did not die in the next coming 6 months. So this is this study has all the patients who had breast cancer, and they can be males and they can be females, so on the x-axis we've got two variables, gender and stage of cancer. Now, if you can note this, gender is a categorical variable, while cancer staging is one of the continuous ones. It can be an ordinal one, but for the sake of understanding, I've made it a continuous one in this example. So we've got two different types of variables on the x-axis, and on the y-axis we've got mortality, yes or no. So what we are doing essentially is that we're taking these three variables, or in fact we're taking two of the variables on the x-axis, and we are trying to predict whether a patient dies or survives in the next 6 months. So this is another model of analysis that we can do based on the type of outcome. So in this case, it's a categorical outcome. Now, so what are some of the tests that are performed for these different types of outcomes? Now, Bivariate test for the continuous outcomes. which are these. So there are different tests that we can do. Pearson's correlation or Spearman correlation for non-parametric distribution. We've already discussed this in the earlier videos. One variable t-test, we will perform that in the example SPSS, where we take a single sample, which you already have, and we compare that against the noun mean, which is selected by you. Students or independent t-test sample, or Welch t-test basically. This is one of the most commonest tests which is used for two independent samples, and it is basically comparing their means to see whether there's a difference or not, and whether that difference is statistically significant or not. Welch is basically a variant of independent t-test, and it's used for the samples which have unequal variances. And SPSS by default runs it automatically. Mann-Whitney's U-test is the other form. Now I've grouped these two together because they more or less act in the same way. So they're comparing independent samples, but student t-test assumes that the samples are normally distributed, while Mann-Whitney U-test does not assume the same thing. So it is mostly for non-parametric samples. Paired t-test is basically the comparison of a given sample before or after a given intervention or time period. For example, blood pressure of a group of patients, at time 0 and after 30 minutes. So we are looking at the same variables like the blood pressure, but we are looking after a time period or after an intervention. Wilcoxon Ranksum test is similar as paired t-test, but it's for, again, non-parametric parametrically distributed data. And finally, analysis of variance, or ANOVA, or a multivariate analysis of variance, or MANOVA. So these are tests basically when we are comparing more than two samples. Like in the above examples, we were comparing two samples and seeing whether there was a difference in means, while in case of ANOVA, we are talking about more than two samples and their comparison, whether their means are more or less similar or there is a difference. And some of the tests for categorical outcomes. Chisquare Test, one of the most commonest and one of the most popular tests, which is done for categorical variables, and it normally compares the counts. Fisher's exact test, this is basically a variant of chi-square, and this is used if you have got less than 5 counts in any of the cells. Fisher's test with Freeman-Halton extension. This is when you're comparing more than 2x2 contingency tables, then this comes into play. And McNemar test, this is a similar kind of a test as we had a look at in case of Wilcoxon Ranksum, but in this case this is only for nominal variables. So if you've got paired nominal data and you want to compare before and afters, then this is the test for you. G-test and multiple correspondence analysis. This is out of scope for this tutorial, but these are some of the other tests that you can try when you're comparing categorical outcomes. So let's get started with the exercises. So let's get started with the first test, which is single sample t-test. Now I'll be performing these tests on this sample data. This is data from one of my research projects, and this is about all the patients who came into the emergency department with complaints of chest pain and presumably myocardial infarction. So we recorded their age, their sex, mean platelet volume, the MPV, before and after 2 hours of some kind of an intervention or observation. We also recorded whether they had diabetes or hypertension, and whether they were found to have an acute coronary syndrome or not, and the criteria which was used to identify whether they had ACS. So this is a sample data which we'll be using. So let's get started with the first test, which is comparison of a one sample t-test. So now what we do in this is that we take one of the variables, like in this case we want to analyze MPV, which is mean platelet volume, and we want to test that against one of the mean values that we choose. Now say for example all the patients coming in with emergency with chest pain, and we have got a hypothesis that the patients who are truly, coming in with chest pain and who have got a myocardial infarction have got a higher MPV, which is somewhere around 12. So we put a value 12 and we compare that value with whatever that is present in the actual sample. So when we run this test, we get these two tables. The first one is telling us about the mean which was found in the population, and the second one is telling us about what we gave it, which was 12, and then it tells us whether it was significant or not. So in this table, the two most important things that you should be caring about to report actually is the level of significance which is obtained, p-value, and the second is the t, which you would be reporting in your final report. So level of significance in this case is less than 0.000, which means basically that indeed there's a difference between the population mean of MPV versus what we give as our mean, or our hypothesis mean actually. And this table also gives you the confidence interval values, the lower and upper bounds, and the mean difference. Now let's run the other tests. The second thing that we'll be doing here is the independent samples t-test. Now for that to happen, you need to go again to compare means and choose independent samples t-test. And say for example, we want to compare whether MPV among males is different than the females among all the patients coming in with chest pain in emergency. So what we do is that we choose MPV from this column and we put it here, mean platelet volume, and then we choose the other variable across which you will be comparing, gender in this case. So we want to compare between males and females. So in the grouping variable section, you have to put in the gender or whatever that you want to compare across. You need to click to the define variable section and you need to mention the types of the two categories of the categorical variable. And once everything is set up, you press OK. And we get these two tables again. The first one is again group statistics, which tells us about the mean in males versus mean in females. And the second table tells us about whether this is statistically significant or not. Now in the second table, I would like you to start with this first section, which is Levene's test for equality of variances. So it simply tells you whether the two samples that we are testing, the males versus females, have equal variances, or is there a difference in variances observed. Now so what you need to do is to start with the level of significance. In this case, as you can see, it's much more than 0.05. So that means essentially that the variances were more or less similar. So in a sense, there was no difference in variances between these two samples. Now if that's the case, you need to look at the first row of this table. But if that was not the case, then you should have been looking at the second row. So we'll just look at the first row. The two important values that you need to know here again is the t-statistic and the level of significance. Now as you can see, the level of significance is much more than 0.05. That means that there is no difference, no statistically significant difference of means between males and females if you're looking at the means of MPV, mean platelet volume. And it's also proven when we look at the mean difference here, which is very negligible or very less compared to the population size that we're talking about. Right, so let's get on and let's see the next test, Mann-Whitney's U-test. So this is for non-parametric populations. So for this test to happen, you need to go to Nonparametric Ttest, Legacy Dialogues, and from here you need to choose two independent samples. And the rest is pretty much the same. You need to select the MPV in the test variable list, and then you need to select the grouping variable, which is in this case gender. We've already selected that here. In defined groups, you need to mention the two categories. In this case, 0 represents female, 1 represents male. Once that is done, you need to select Mann-Whitney U and you need to select OK. And it's more or less a similar test. It gives you, so instead of giving means, this is now giving you mean rank. and then there is a comparison between these two mean ranks. The important table that you need to look and report will be this one, where you should be looking first at the asymptotic level of significance, which is more or less, in essence, you should be considering it as being the same as the level of significance, which is p-value. So this is again 0.8, much higher than 0.05. So that again means that there is no statistically significant difference between the two populations. So let's have a look at the paired sample t-test. Now for this example, we'll be taking these two variables, MPV and MPV2. MPV is the mean platelet volume of the patients who just came into emergency, and MPV2 is the MPV of the same patients taken after 2 hours of some kind of intervention or observation. So we want to say whether there is a statistically significant difference of MPV 2 hours, into their admission into ED. So for that, first you need to go to compare means and then choose paired samples t-test. Now again, we are assuming that the two populations have got a normal distribution, or more or less the normal distribution. That's why we are choosing the paired sample instead of the Wilcoxon ranksum. So from here we need to just choose the first variable and then the second variable. The first one will be at time 0, the second one will be after 2 hours, and then we need to select OK. So again, it gives us these three tables in this case. The first one is basically the mean statistics, some of the correlations basically. So this is a simple correlation between the two variables, and then the most important one will be this one. Again, here you need to start first with the level of significance on the far right here. So 0.3, much more than 0.05. That means apparently there is no difference pre or post 2 hours, into emergency admission. So apparently there is no difference between these two populations. So let's see whether we can do the Wilcoxon ranksum. So again, you need to go to Analyze, go to Nonparametric, Legacy Dialogues, and from here you need to choose Related Samples. So this is Wilcoxon's ranksum test. It gives you a similar kind of a dialogue, and you need to choose the two variables, MPV1 and MPV2, pre and post, and then you need to choose Wilcoxon here and press OK. And it more or less gives you a similar kind of a table as before. Again, mean ranks have been given. Now in this case, as you can see, it is telling us that there are 155 ties. That means pre and post, 155 pre and post values were similar. And there are some negative ranks, which means that there are 15 values in which MPV1 was less than MPV2, and there are 17 in which MPV2 was greater than MPV1. Now the important table here in this case again is this second one, where you need to look at this asymptotic level of significance, which is again much more than 0.05. Apparently there is no difference between the two populations. Now we would normally choose the first paired sample t-test if we know the sample is normally distributed. In the other case, if it's not, then you should be using Wilcoxon sign rank tests. And we already have explained how to see that distribution and how to calculate the exact distribution parameters in some of the earlier videos. So let's go and see the next test, Chi-square test. So one of the most common ones and popular ones. Now chi-square is basically a comparison between the two nominal variables, and it's basically a comparison of counts. To do it practically, go to Analyze. In this case, you need to go to Descriptive Statistics, and you need to go to Crosstabs. And here you need to choose the two variables that you want to compare across. Let's say that we want to see whether gender is predicting the presence or absence of diabetes or not. So in this case, you can put any of these variables in either rows or columns. Mostly it doesn't make a lot of difference for the effect of the test, but just to make things visually easier, as we explained before, let's put diabetes in rows and let's put gender in the columns. And if you click onto the first options button here, in fact, let's click onto the second one, you get these options. So we are simply doing a chi-square test, but if you knew that this was a pre-post test of nominal variables, or a paired test of nominal variables, you could have chosen McNemar test from here. But in this case, let's select the chi-square test and let's press OK. Now we get these three tables. The first one is just telling you the comparison among the variables that we have selected. The second one is just telling you the same 2x2 contingency table. It's showing you that with total subtotals at the end. But this is the table that you need to look at. Now this table by default has done a lot of tests for you. It has done Pearson's chi-square test, it has done a likelihood ratio comparison, it has done a Fisher's exact test, and some of the other ones as well. But what you need to look at are these two ones. Basically, the first one is the Pearson's chi-square and the second is the Fisher's exact test. So these are the ones that you should be really interested in. Now Pearson's chi-square test should be your first go if you know that your tables don't have less than 5 observations or counts in them. So in this case, as you can see, 37, 70, 29, 52, all of these counts are way above 5, so we can go with the first choice. But if any of these cells had lesser than 5 count, then we should have gone with the Fisher's exact value. So in this case, as we can see, the asymptotic level of significance, which is again the p value, is much more higher than 0.05. That means essentially that there is no difference between males and females for the presence of or absence of diabetes. So apparently gender by itself does not make a huge difference whether the patient has diabetes or not. We apparently have gone through all of these tests one by one. I was a bit quick, so I apologize for that, but the fact of the matter was that I wanted to keep the video as short as possible, and as to the point and focused as possible. So if you've got any questions about any of the things that I've explained, you're most welcome. You can go to my website here, or you can leave your questions in the comments below. And this is one of the websites that I've mentioned here. It's a very useful and helpful website if you want to know how to interpret and how to write the interpretations in your research papers. So this is the website that you should check out. Thank you so much for joining again, and I will see you again with the next video. Ciao for now.